We stopped here. I think we went through now, and so this is very important. I mean, this slide is very important, except that of course it's missing they have the neutrals connected, but they don't have impedances between the neutral and ground. Okay, so anytime there's an impedance between the neutral and ground on the primary, what do? Add a 3Zn. On the secondary, so here you would have added a 3Zn. Here you would have added a 3Zn. Here you would have added a 3Zn. Here you would have added another 3Zn. And that's it. Okay? So any questions on those? Okay, so now do we see how transformer and let's see. So for the transformer, you will be given the impedances, the Z0, Z positive, and Z negative. You will be given these impedances. The Z positive and the Z negative are really the impedances of the transformer, because again, they're the same. I mean, it's if you apply, if you switch the two phases on a transformer, nothing will change. The impedance will be the same, right? So Z positive and Z negative will be the same for the transformer. Z0 will be different. You will be given that. It's not like the transmission line where you were no, not like the transmission line where we calculated it to be ZAA minus 2ZAB, right? Here for the transmission line, for the transmission line, Z0 was ZAA plus 2ZAB, Z1 and Z2 were equal ZAA minus ZAB, right? This was different. For the load, it was the same, right? It was just a Z star, Z star, Z star, right? So for the load, it's the same, but you just add 3Zn if you have a neutral impedance. So we have load, we have transmission. So load is the same. Transmission line, I just showed you Z0 and Z1 and Z2. Generator, you will be given those impedances. You will be given those, and then sometimes you will be given more than one positive sequence impedance actually. So this is important because the positive sequence impedance in the generator takes on several values depending on the value of current in the generator. So initially, when at the inception of the fault, the current becomes very, very high, right? Current leads to flux in the air gap, leads to a certain amount of armature reaction, leads to a certain value for synchronous impedance, if you remember from the 338, right? It's a value. The inductance is what? Inductance is, again, you have currents in coils and magnetic fields around them. So if the value of the current is very large, the value of the inductance will change, right? You remember L is equal to the delta lambda over I, right? So from 438 or from our discussion here in this class when we were calculating the inductance, so it depends on the amount of flux. So it will depend on the amount of current. So the generator goes through sort of what is called a subtransient period, a transient period, and a steady state period during the fault. So it's a subtransient. You will be given a subtransient. That's why the problems sometimes you will be given. You will read the word in the homework I will assign. You will hear the word, subtransient synchronous impedance, transient synchronous impedance, steady state synchronous impedance. All of those are the same positive sequence impedance for the generator. So if we look at the generator's impedance here, actually they may discuss those here. No, I don't know. I don't think I put it on the slide. Did I? No, I didn't put it on the slide. But the value of positive sequence impedance sometimes will be given as, so during a fault, the Z plus approximately equals Z minus. The Z0 is then substantially smaller, but no, we don't talk about, I don't talk about the subtransient, transient, and synchronous, and the steady state values for the impedance. But the difference between them is the subtransient impedance is at the inception of the fault, right at the inception of the fault when the current is the highest. The transient synchronous impedance is a few cycles later. The steady state synchronous impedance is the steady state value of the machine's impedance during the fault. Right? So as long as the fault is maintained, there will, and during steady state, you will have fault current will do something like this. It will become very high and then slow down and become, go to some steady state value of current. Right? So this is where the steady state synchronous impedance value is. This is, a few cycles after the very high peak current. This is where this is the steady state synchronous impedance is. So this is subtransient, and this is transient. Okay, so the subtransient impedance will be the least because it's the highest current. Then the transient impedance, then the steady state synchronous impedance. Okay, so you may be given several values for the positive sequence value of the impedance here. Anything? This is really what I wanted to discuss here. So we are okay with the machine model in symmetrical components. The motor and synchronous motor is like a synchronous generator exactly. The synchronous induction motor is exactly the same, but you remove the voltage source unless I tell you it's a high power motor and I give you a pre-fault voltage, for example, to utilize, right? Then because a very high power motor will have significant inertia, so it will continue to rotate and feed the current, the fault with some current for a short period of time, maybe at least during the subtransient period. So during the subtransient period, this machine may have some source here, right? And it will be given to you if needed. Yeah. Transformer, again, as soon as you see a transformer, I would say go to this slide. As soon as you see a transformer, go to this slide, except for, of course, the fact that the 3ZNs were not included here, the neutral impedances. So you see a transformer, you have to substitute it with the proper equivalent circuit based on the connection. Right? Because this will then determine the contribution. If I ask you what is there's an example here in the next chapter. Okay, what is the contribution of the generator to the fault? What is the contribution of the transformer to the fault? What is how much of the fault current flows through the transformer? Right? Maybe nothing. Right? So if the fault is right here, right, then nothing is flowing through the transformer. What is the transformer's contribution to the zero sequence component of current during the fault? Right? Nothing. But positive sequence, it will have. Because what is the model for the transformer in positive sequence? Yeah, it's this. It's a short circuit. So you go to the positive sequence representation and the negative sequence representation are an impedance, just the phase impedance of the transformer, in per unit, of course. Right? The zero sequence will include the 3ZN on both sides if it has an impedance on both sides. Or it will be one of these other ones that we just saw here. Okay?
Should we know this for the exam?
I think it's on your equation sheet. I think check your equation sheet. I mean, you will find out from your homework if it's on your equation sheet or not. I think it's on your equation sheet. Yeah. So she has everything. Wow. Very good. It's on the equation sheet. Yeah. So I mean, you don't need to memorize it, but really once you do it a few times and you understand, okay, star, if there is a neutral impedance, zero sequence current will flow on the primary. Is it going to flow on the secondary or not? You look at the secondary side. I mean, I think if you go and reason to yourself through it, you will not need to look at it, but it's included there. So basically, what we're going to do is have a system, and that's what we're going to do next. Yeah, show you a system and build the sequence circuits for this system. And then what do we do with them? That's what we're going to do also as well in the next chapter. Anyway, so the last slide in this chapter is talking about power. Okay, without looking at this slide, okay, I have a system I chopped up into positive, negative, and zero sequence. if I'm trying to calculate the power delivered by that system, what do you think we will have to do? I will have to calculate the power in the positive, negative, and zero sequence circuits, and then and that will be the power in one phase. Multiply that by 3, and remember, because it's for one phase. Yeah. So this is S phase. S phase will be no, so this is a total. So the total here is phase A plus phase B plus phase C, right? But then you will calculate phase A, I guess, by itself. Phase A we will chop it up into 3 sequence components. You can calculate the power from there, from the phase B, and then from phase C. So anyway, this is power in phase quantities equal to voltage times the current conjugate, voltage times the current conjugate, voltage for the 3 phases, right? So we can write that in matrix form as two vectors, and then we can convert the matrix. Again, we know the relationship between V phase. So this is phase quantity for voltage, phase quantity for current, right? We know the relationship between phase quantity for voltage and the sequence quantity for voltage. The phase quantity for voltage equals A times Vs, and the sequence sequence quantity for current is equal to A times Is. So we remove V phase and put A times Vs. Remove I phase, put A times Is, and we end up with V sequence transpose equals A transpose times A conjugate multiplied by I sequence transpose, right? So that will be the total power, because it's the sum of the power in all 3 phases, right? So what is A transpose times A conjugate? This is A transpose times, it's 3. Remember, it will be 3 times the zero sequence circuit's power, because each zero sequence circuit is for one phase. Right, I have a zero sequence circuit for phase A, zero sequence circuit for phase B, for phase C. So I have to take that multiplied by 3. Take the positive sequence multiplied by 3. Take the negative sequence multiplied by 3. Right, that's where these 3's come from. I mean, they mathematically show up, right? And it makes sense that they mathematically show up, but this is where it comes from, right? Because it's 3 of the zero sequence circuits, which represent the zero sequence circuit for phase A, for phase B, for phase C. Okay, so they just multiply those out here. So they take the 3 out, 3 outside. So, and they just rewrite the power in terms of sequence quantities, right? So it's 3 times the power of the zero sequence circuit. Remember, because each of these circuits now is a balanced circuit, right? In the zero sequence circuit, I have voltage. All the voltages are equal in the zero sequence circuits, and all the impedances are equal, which means all the currents are going to be equal in the zero sequence circuits for all the phases. So take one of them multiplied by 3, right? Same thing for the positive and same thing for the negative sequence. We're okay? So S phase, the full power of the full power of a 3-phase system is equal to 3 times the power of the 3 sequence circuits, right? And that's what we have here. So any questions on this? So this wraps up chapter 8. Chapter 8 is really nothing but, build the sequence circuits. It doesn't really tell you, okay, what do you do with them, right? So now, now we'll see with the next chapter, what we'll do is, we'll now apply what we've learned to a useful problem, actually. So what is the use of what we did so far? This symmetrical components, what we said is, it allows you to analyze an unbalanced system, right? So when we talked about unbalanced systems briefly, we said that, so this chapter is called unsymmetrical faults. Unsymmetrical faults are an example of an unbalanced system, right? So, we said that 3-phase faults, they are nothing new to what we've been doing before. If you have a 3-phase fault or a 3-phase fault to ground, they're the same as what we've done before. It's nothing but analysis of your positive sequence circuit, because it's a balanced fault. All the 3 phases are connected to each other. As soon as the 3 phases are connected to each other and they see the same impedance, the source sees the same impedance on all three phases, it's a balanced system. Fine, the fault current is much higher than the regular load current, but it's still a balanced system. So you analyze it the same way as before. Draw the single-phase equivalent circuit. And that single-phase equivalent is actually the positive sequence circuit. And we know that in symmetrical components, if the system is balanced, you will only see the positive sequence circuit. Or if you flip the power terminals, then you will only see the negative sequence circuit. Right? And both of these circuits are balanced three-phase circuits. And they are nothing but the single-phase representation of your circuit that you've seen before. So for the transformer, it's a series impedance. In the positive sequence circuit and the negative sequence, they're the same. They are exactly the same. For a transmission line, we saw that they're the same. The Z1 and Z2, the positive and negative sequence impedances were exactly the same. Makes sense because it's a balanced system. It does not really matter if you flip the windings. Right? The only difference is the generator in positive negative sequence is that there is no source in the negative sequence, because if you want to flip the terminals, you put the source where? In the negative sequence circuit. Right? Well, if you will flip the terminals, yes, that's a good point. If you flip the terminals of the generator and you're supplying a load using negative sequence, then I'm telling you, don't put the source on the generator's positive sequence circuit, put it on the negative sequence circuit. Right? The model for the generator was a source on the positive sequence circuit. Correct? I'm telling you, no, I'm supplying my load using negative sequence. What does that mean? That means that the source that's in the equivalent circuit is going to be placed in the negative sequence, not the positive sequence. Yeah. Okay?
So I'm just curious. So if you replace the AC source with the DC one, would it be the zero sequence?
You replace the AC source with the DC one? Will it be the zero sequence?
Yeah.
But it doesn't really apply because for DC, all the impedances are what? Inductors are short circuits. Capacitors are open circuit.
Yeah.
So you don't. There's the DC power flow has resistors, a bunch of resistors. It's very different than what we are doing now. There will be no phases anymore. In DC, there is no phases anymore. So this whole there will be no meaning for conjugate. It's very different. The DC power flow is different. And DC power flow is like our circuit analysis. Yeah, I mean, we can study DC power flow, but it's not something we study in this course. Yeah. No, it's very different. Yeah. No inductors, capacitors, open circuit. It's just a bunch of resistors. Yeah. Okay, so the beauty is now we can analyze unbalanced systems. Unbalanced systems are systems where there's an extra load on one of the phases versus the others. There's a fault on one of the phases to ground. There's a fault between two phases up on the transmission line, on the transmission tower. There's a fault between two phases and then on the ground. These are all examples of unbalanced systems. Yeah. So how do you analyze those? You have to utilize symmetrical components, and faults is a good example, is a good thing to is a good way to apply symmetrical components, or is the most the biggest reason why we study symmetrical components, because we want to understand how to protect the system. How does the system behave? So I can place the current and voltage sensors in the right places. That's really the objective of what we're going to try to do here. Okay. So we will talk about three main types of faults: a single line to ground fault, a line to line fault, a double line to ground fault, or a line to ground fault. Yeah, these are the three types of faults we're going to talk about, because three-phase faults, we said they are balanced, right? They're balanced faults. So we know how to do this. Yeah. I will skip this topic. It's the last two slides of this chapter. It's not as important. So. Okay, so what we will find is that when we try to analyze faults, what we did in the last chapter was what we did. We did this. For example, let's say we have a system where we have a generator here, a transformer, a transmission line, and a load. And I said this load is just star connected with no neutral. This is star, neutral connected, no impedance, and this is star, yeah, just star connected, no neutral impedance. So what's the positive sequence circuit of this system look like? Generator, the source, and if I give you the positive sequence impedance, you put it for the generator, right? If not, then you don't put it. And then for the transformer, if assuming I give you the impedance, I give you the per unit impedance, then you put the per unit impedance in series, or if I tell you ignore the series impedance, it's a short circuit. Transmission line, same thing, impedance, and load, same thing, impedance, or RL if I give you the power factor, for example. But assume it's just a reactive load for now. Then this is the positive sequence circuit. Negative sequence circuit. The generator, I said, is a healthy generator. There's no negative sequence component of voltage, right? So there's no voltage source in the negative sequence circuit. But there's a negative sequence impedance if you are given that. And then the transformer, again, we said positive and negative sequence are balanced. So negative sequence impedance comes from the fact that you have a balance. If you apply a positive, balanced three-phase voltage across this transformer, but you flipped two of the phases, you're applying a negative sequence. What will this power source see? It will see the same series impedance of the transformer that you saw before. It will see the transformer's impedance, whether you have the transformer connected in positive sequence, flip the terminals, you will still see the series impedance. Ignoring phase shift, okay? Forget about phase shift. Here I put star. Okay? And then transmission line, same thing, but it will have a different value than the positive and negative sequence impedance will also have the same value, as we saw from the last chapter. Then the load will be like this. How about the zero sequence circuit? Open up your equation sheet. Come on. Open up the equation sheet. Generator. It has no source. There is no connection to ground. Since there is no connection to ground, that means that I don't have zero sequence current flowing. It's an open circuit for zero sequence. And then it will have a zero sequence impedance, if given. Okay? And then transformer. What does this transformer look like in zero sequence? It's star with neutrals both grounded with no neutral impedance. So what does it look like, Sarah? Exactly. It's nothing but an impedance. It's a zero sequence impedance of the transformer. There's no open circuit, no tricks at all here. Right? And then the transmission line is also an impedance. There's a load here, sorry. And then the load is what? Star connected with no neutral connection. So what do I see? Exactly. I will see the load's impedance, and then I will see an open circuit. Right? So this is the positive, negative, and zero sequence circuits. Here, from these circuits, okay, is anything going to flow in here? Any current going to flow in this circuit as it is by itself? No. How about this? No. Here? Yes. Right? But now if I tell you there's a fault here at this bus, okay, and we said that the use of this thing is to allow us to analyze unbalanced systems. So fault here, and this is a single line to ground fault. One line to ground, single phase to ground fault. Okay, so one of the phases fell to the ground. One of the phases is consuming a lot more current than the others, right? So, for example, okay, so in that case, this is a case of unbalance, right? So how are these helping us? The way they are today, the way they are now, how are they helping us?
The negative and zero sequence wouldn't be affected.
But if the negative and zero sequence don't have values, we said that, and the only thing that we have is the positive sequence, then we said it's a balanced system. right? Didn't we say that? Huh? Yeah, I did. No, I know, it's true. So what?
A short or yeah, in the positive sequence.
Uh-huh. What?
Short on the bus to
Here?
yeah.
Yeah. So, but this is remember, this is the single phase or the single line representation of a three-phase system, right? Or this is the single phase representation for the positive sequence of phase A, for example, right? And it's also the single phase representation of the positive sequence of phase B, right? So if you put a short here, are you going to put the short on phase B and C? No. No, you cannot, because the fault is only happening on phase A. So are you going to put a fault only on the positive sequence of phase A and then not do that on the positive sequence of phase B and C? But then how do you analyze that? Because you will still end up with the negative sequence and zero sequence not having currents, right? But we know that if it's a single line to ground fault, do I expect to see zero sequence current or not? Well, from the discussions we had, I said that anytime you have something connected to the ground, meaning current flowing from the neutral to the ground. Connected to the ground meaning, how can it be connected to the ground? It will be if there's a single line to ground fault here. So this is my star, for example, and this is my star here, for example, and this is my transformer here. So I have, this is grounded. So I said one of these lines, one of them, has a fault to ground. Right, it's connected to ground, so the current will flow here, right, between this, in this loop, right? So current will flow from the neutral, right? Current will flow in the neutral. Do you agree or not? If there's a fault to ground, current will be flowing in my neutral through the ground circuit, right? If current is flowing in the neutral, what does that mean about the zero sequence current? It will exist. There will be some zero sequence current existing, right? So I cannot leave these three circuits by themselves. So these three circuits are representations, the sequence representations of these three-phase systems. Okay, so they are. It's true, nothing wrong with that. But for us to analyze a case like this, we will have to connect the three circuits somehow. Right? If I connect them somehow, if I figure out, if I find a mathematical way to connect these three circuits, then let's say I connect this to here, and I connect this to here, for example, and I connect this to here, for example, okay? If I do that, then, fine, current can flow out of my generator. Okay, now it has the fault here, right? So it can actually, current can flow here, current can flow here, current can flow here. If this fault current can flow, oh wow, it finds a path here. So it can find a path, it can also find a path here, right? And it can also find, cannot find a path here. So this is probably not the right way to connect this circuit. Okay, so but the idea is, if and we will figure out how to mathematically connect these circuits. Okay, so like we figured out how to mathematically derive these circuits here, right? We will figure out how to mathematically connect the circuits after, okay, we built the circuit. How do you connect them? So the idea is we need to figure out how to connect these circuits are okay. We just need to figure out how to connect them to be able to analyze this case, the single line to ground case, or the double line fault case, or the double line to ground case. So it's the two phases connected to each other case, or two phases connected to ground case, or one phase connected to ground case. So it's just three phases, three cases, right? So we don't have any. These are the three cases that summarize power systems. There's no other case. Yeah. So, and that's what we're going to be looking at in this chapter. So, When an unsymmetrical fault occurs in a balanced system, the sequence networks are interconnected at the location of the fault. That's what this says. So how do you interconnect them is what we need to learn in this chapter. As such, the computation of fault current is greatly simplified. If I interconnect them somehow, like the way I did, do you know how to solve it using your hand? Let's say I connected them in series, for example, the way we just did. Then it's find the equivalent impedance, right? And then divide the voltage by the impedance that it sees, right? And it's exactly like solving a single phase equivalent circuit, right? It's simple. It becomes a simple thing to solve. You don't have to do all the loop currents in the three-phase systems anymore, right? So how do you do that? We will, again, typically when a fault occurs, there's a, as I said, there's a subtransient period, transient period, and a steady state fault current. These are, I'm not referring to steady state current, load current. There's a steady state value of fault current, there's a transient value of fault current, there's a subtransient value of fault current, And again, we talked briefly about those at the beginning of the class. There's, in addition to these these values of impedances corresponding to these subtransient, transient, and steady state fault periods, there's also a DC offset associated with the fault current. So again, I will not. Again, we do not analyze the transient performance of power systems in this course. So it's mainly related to steady state. So we will ignore this DC component. But it's good to know. It's important to know that we have that the impedance of a generator during the fault goes through different values, and you will typically have to select. Again, when you have a very high current flowing in the system, current. Remember from your 322 class, for your electromagnetic class, if you have two bars with currents flowing through them, there will be a force generated. Right? There will be a force. There will be a force generated. This force that's generated is something you have to account for in the mechanical design of your equipment. Right? So you will typically have to, if your fault current is 1,000 or 10,000 amps, there will be a force on the bus bars inside your cabinets, inside your substations that you have to account for. That's why the subtransient impedance is an important consideration. So you will typically use the subtransient impedance in your fault calculations when you are trying to select the circuit breaker's peak current. Right? The circuit breaker has a short circuit capability. The short circuit, it's not the steady state value of fault current. The steady state value of fault current will do what? It will raise the temperature. Right? There is lots of losses. It will raise the temperature considerably, and it will burn fuses. It will do that, right? But the subtransient part will do what? Will be the one that is really going to do all the mechanical forces on you, right? If it's the subtransient is only for a very short period of time, just at the beginning, you have to account for that because it's going to create all these strong forces. So you have to account for that in the short circuit rating of your equipment, right? The steady state is fault value of current is okay. This is this is the steady state value of current that will remain in there until you clear your fault. You don't want your system to burn down, because this is going to stay there. This value of current, the subtransient will die away. It will decrease. The subtransient current will decrease, right? And then you will be left with the steady state value of fault current. The steady state value of fault current will cause temperatures to rise, arcs to occur, all of this stuff. Right? That's what's going to happen there. So there's a steady state fault rating of equipment. So when you select a circuit breaker, you will have to consider the peak value of short circuit current as well as the steady state value of short circuit current. One will be used to select the short circuit rating of the equipment, and one will be used to select the steady state fault value. So steady state current breaking capability of the equipment, right? So there will be two things that you will be interested in selecting circuit breakers in.
It's not peak voltage?
No, voltage is zero. I mean, voltage is important because, again, in a healthy case, your circuit breaker is open, right? Sorry, in the healthy case, your circuit breaker is closed, right? If it's closed, and you're connecting to it, and the circuit breaker is also grounded. I mean, the structure of the circuit breaker is grounded, so you have to make sure that your all your contacts versus ground are insulated properly. So that, but voltage during the short circuit is not really a consideration, because voltage, when a short circuit happens, the voltage drops down. Right? So voltage is an important consideration, but it's mainly during operation. Okay. And it's important also when the breaker is open. When the breaker is open, then it's like an open circuit. At the terminals of your circuit, then you will have the full voltage. So it's voltage and current. I mean, it's okay. We talked about the representation of the system, and we will do an example. So some of the things that are important, for example, if you have a single phase to ground fault, the current in the phase that has a fault is going to be much higher than the current in the other phases, correct? If it's a fault current, if it has a fault, the current in the other two phases will be the regular load current. So there will be a huge difference between those. So when we analyze, what we're trying to do is come up with a mathematical way to connect the circuits, right? So for us to come up with a mathematical way to connect the circuits, there are some assumptions. So one of the assumptions that we will assume is that the phases that do not have fault currents flowing through them will have a current of 0. That's one of the assumptions that we will use. So this is, for example, pre-fault load current is neglected. This is what this means, for example. It will be something that's a consideration that we want. It will be helping us to come up with a way to connect the circuits. So this is probably the most important one. The power system operates under balanced steady-state condition before fault. Thus, the positive, negative, and zero sequence networks are uncoupled before the fault, right? Before the fault, the sequence networks are uncoupled. Right? They're uncoupled sequence networks. When the fault occurs, we will have to find a way to couple them, and they will be coupled at the fault location. Right? So when I said that, we will couple them at the fault location. So the fault is between this bus bar, at this bus bar, between this bus bar and ground. So this is the fault location. This is the fault location. This is the fault location. Right? This is the fault location. So how do you connect these circuits at the fault location? Is what we're trying to find out. Okay. Transformer winding resistances and shunt admittances. So again, we ignore the shunt admittance for the transformers line, series resistance. We're going to ignore the series resistance of the transmission line. That's what we've been doing anyway. And we're going to ignore the shunt admittance of the transmission line, right? So we're only going to ignore the series. We're going to include the series reactance of the transmission line, not the resistance, right? I mean, this is stuff that we've been doing before. Induction motors are either neglected if they're small. Induction motors are either neglected or represented in the same manner as synchronous machines, right? So they will either be an impedance, or there will be, in the positive sequence, there will be like a voltage source, like a synchronous machine, right? Yeah, we did, in the synchronous machine model, we ignored, resistance, we ignored, saliency, saturation, and we just represented the machine model as what? A voltage source with a reactance in series, right? I didn't care about saturation, I didn't care about saliency, I didn't go into the machine design. Oh, fine, we represented all of the inductances in the machine by an approximate synchronous reactance in series. Period. That's it. For power system perspective, this is enough. If you're going to be looking into the protection of a synchronous machine in detail, then you may want to look at a lot more detail about the machine, like the transformer. If you want to be looking at the transformer's protection, you may be interested in the shunt, the value of magnetizing current, for example. Here, I don't care. Right? I really don't care for that. Yeah. Anyway. Phase shifts can be considered. for the star delta, that they can be considered. It's like what we did before. You will include your transformer. If there's a phase shift, if this transformer is a star delta transformer, if this transformer is a star delta transformer, you will include, if it's a star delta transformer, let's say here with a star, with ground here, and then it's delta. So what's the representation for that? Sarah, since you have your equation sheet. No, I don't care about positive sequence. Positive sequence, yeah, let's do positive sequence. Positive sequence will be what? Impedance. No, positive sequence will be impedance of the transformer, and then the phase shift, the ideal transformer, right? This is the positive sequence representation. Do we agree? That's what we did before. Don't have what? Yeah, but because here they don't consider phase shift. But if you're going to consider phase shift, you do what we did before, right? I mean, it's the series impedance. In there, what is it in the positive sequence? It's only a series impedance, correct? Mm-hmm. So if you ignore the transformer phase shift, it's a series impedance like this. If you consider transformer phase shift, you have to include this, and this is the star side e to the j30 to 1, right? Mm-hmm. How about negative sequence? Series impedance, ideal transformer, but we have to flip the e to the j30th, right? Negative sequence, remember we're flipping the e to the j30th? Go back, review transformers, review chapter 3. We were flipping the phase shift for the negative sequence. If you apply negative sequence, we did that in example in class. How about for the zero sequence? Now it's what you're saying will come into play. The series sequence, zero sequence will be what?
Based on the paper?
Based on the paper.
It's like a series impedance, and then there's a short circuit, and then there's a
right, so that will be the case for the zero sequence. Do I care about, there's no ideal transformer anymore because there's no phase shift between primary and secondary on the zero sequence, right? It's open circuit on the zero sequence, and there's nothing happening there. Okay, so the zero sequence current will only flow here on the primary. Is this okay? Okay, so the way we will do it is the following. At the fault location, we will find the Thevenin equivalent circuit. Everybody's okay with that? So that's what we'll do. So that's the process. So at the fault location, so here I will stop. I will go. Where's the fault location? Bus bar 2. This is bus bar 1, bus bar 2, bus bar 3. The fault is happening on bus bar 2. I will go to bus bar 2. So here, this is where the fault is happening, and I will find the Thevenin equivalent circuit seen from these two terminals for the positive sequence circuit. Thevenin equivalent circuit seen from these two terminals for the negative sequence circuit. Thevenin equivalent circuit seen from these two terminals for the zero sequence circuit. Okay? So I will do that, and then we'll figure out how to connect them. So first I will find the Thevenin equivalent circuit for the zero sequence network. It will be, since I know that there's no voltage source from the generator, then it will be an impedance, period. The positive sequence, there will be a Thevenin equivalent voltage source, and there will be a impedance. The Thevenin impedance, the Thevenin impedance that we have. And same thing with the negative sequencer. There's no voltage source, there will be a Thevenin impedance. So I will always end up with a Thevenin equivalent circuit for the system between between the two nodes where the fault is happening, right? So, and then I will need to connect these somehow. How to connect them will depend on the type of fault, right? So do we see the process now? I will come up with a Thevenin equivalent circuit for the system, and then I will figure out how to connect them. So yeah, here we're just reviewing, for the generator, this is what the generator looks like, positive, negative, and zero sequence. Transformer, star star connected, this is what it looks like. Transmission line. So the summary of the procedure is come up with the sequence networks for the system, find the Thevenin equivalent at the fault point. The Thevenin equivalents are then connected using relationships between the sequence currents and voltages, which we're going to come up with right now. And then if you've connected them somehow, if you've connected these circuits, let's say I connect them somehow. Let's say I do this, for example. Let's say I do this. If I connect these somehow, okay, am I going to have current here or not? I will. The current will flow out of the source through here. Back to the source. Right? So now I know my zero sequence current, because this is my zero sequence current. And I know my positive sequence current. I know they happen to be equal if I connect them this way, right? So if we take our three-phase circuit, use our assumptions that we have on the initial slide, only the phase with the fault happening through it will have current, the others will have zero. Use those assumptions and see mathematically what do the sequence circuits look like in that case. If they end up being something like this for one of the cases, then here in this case, I know that the sequence current, positive, negative, and zero sequence currents are the same. What else do I know? I know that if this is my fault impedance, for example, let's say this is my fault impedance, Z fault, I know that the current flowing through my fault impedance will create a voltage drop, right? We'll have a corresponding voltage drop. If this happens to be my fault voltage, then I know that my fault voltage is equal to what? The zero sequence voltage plus the positive sequence voltage plus the negative sequence, right? These three voltages are equal to this, in this configuration only, right? So we'll see what the different configurations lead to mathematically, and then we'll connect the circuits, right? But so everybody's comfortable with doing Thevenin equivalent circuit for a system, a small system like what we showed, right? Then how do we connect is what we're going to look at now. So forget about this. Let's do an example. I think this is a good example. So here, this is a example. I think they're going to ask you to do what? They will ask you to, if you have a single line diagram of a power system where negative and zero sequence reactances are also given. So they're giving you the X double prime is a subtransient impedance, right? Remember we said the positive sequence impedance can take on three values. So they may not tell you, okay, positive sequence impedance. They will tell you subtransient or transient or steady state synchronous impedance. All of these three refer to the same thing. They refer to the positive sequence impedance. They're all the same, right? So they gave you here the positive sequence impedance, the negative sequence impedance, and the zero sequence impedance for the generator. Then they gave you the impedance for the transformer per unit. This is a positive, negative. We'll find out now. Then they gave you the positive, negative, and zero sequence impedance for the transmission line. Then they gave you the impedance of the transformer. Then they gave you the positive, negative sequence impedances for the motor, or in this case, yeah, it's a motor. And they also gave you the neutral impedance because it has neutral impedance connected between the neutral and ground, right? So the neutrals of the generator are delta star connected. Transformers are solidly grounded. So this solidly grounded, solidly grounded, solidly grounded. The motor neutral is grounded through a reactance, blah, blah, blah. Draw the per unit positive, negative, and zero sequence networks on a 100 MVA base, 13.8 kilovolt base in the zone of the generator. So they gave you the base in the zone of the generator. So here it's like starting from chapter 2, right? Because you're going to have to calculate if you're given anything in real values, like here, and you want to convert everything to per unit, you go back to the transformer chapter, right, all the way. And if I ask you to calculate any power, then you're going back to the beginning of the class, right? So a problem like this will cover from the beginning of the semester until now. That's the problem. Right? That's why it has to be cumulative, right? Because of this, right? So, and then what's first I can tell you calculate the current transmission line under balanced steady state conditions, right? Or the generator current under balanced steady state conditions. And then I tell you there's a fault. Then you have to come up with the sequence networks. Then you have to figure out how to connect the sequence networks so that we can calculate the fault current, right? So that's why it's all the way from the beginning. Still have time. Reduce the sequence networks to their Thevenin equivalents as you viewed from bus 2. So we will have a fault at bus 2, obviously. Okay, and they will tell you they're telling the pre-fault voltage VF is 1.05 per unit. So they will tell you that the voltage right before the fault is 1.05 per unit. So it's if you can consider the motor as a synchronous machine, it will have a voltage of 1.05, and the generator will have a voltage of 1.05. So in the positive sequence circuit only, right? Pre-fault load current and delta star transformer phase shifts are neglected. To make your life easy, we neglect transformer phase shifts in a problem like this. And of course, the pre-fault load current is neglected. This is something we need anyway to derive what we're going to derive next. Yeah. So I will not. We can just go through this quickly because I don't want to. I want to go to the next part. So how do I approach this? I want to draw the positive, negative, and zero sequence circuits. Okay, again, this is a generator. In the positive sequence, it will be the voltage source and its impedance. Transformer, impedance. Transmission line, it's an impedance. Transformer, impedance. Load, in the positive sequence, let's say it's a motor. So I will consider its impedance, and I will consider its voltage because they told me the pre-fault voltage is 1.05. Okay, so, and this is bus 2. Negative sequence circuit will look exactly the same, except for what? I will not have these sources. Exactly the same, but I will just not have these sources. Zero sequence circuit will look like what? There is neutral connection. So short circuit for 3Zn. 3Zn is 0. And then I have no voltage, of course. And then I have the zero sequence impedance of the generator. And then this transformer. What does it look like? Delta, star on the other side. So delta, again, delta, zero sequence current cannot flow into the delta or out of the delta, right? So it's an open circuit on the delta side, right? So it's an open circuit. This is my delta, it's an open circuit. How about on my star side? You have the impedance and a short circuit like this, right? From the sheet, from the ones. Yeah, because they gave your no delta to star. Just look at it in the other way. Okay. And then you have a transmission line, and then you have here star delta عشان ما تزعليش. What? So star delta impedance like this, and then open circuit on the other side, and then you have your motor's impedance, and then the motor's 3Zn because it has a neutral connection to ground through an impedance, right? So this is what the zero sequence circuit will look like. Positive sequence circuit, and negative sequence looks like the positive but with a short circuit around the sources, right? So let's look at how they solved it. So they only drew they drew all of them. So here the positive sequence circuit, the two sources, the rest of the impedances, the zero sequence circuit, and the negative sequence circuit. Okay. So for the transformers, they use the same impedance, by the way, for the positive, negative, and zero sequence. They just use the same impedance here. Everybody's okay with this? It's exactly what we drew. No surprises, right? So now, what's the next step? Yeah, now they're telling us that there's a fault at bus 2. There's a fault at bus 2. So you go to every one of these circuits and you stop, put 2 pins like they have here, and then find a Thevenin equivalent circuit between these 2 nodes. What is a Thevenin equivalent circuit between these 2 nodes? And it's open here, so it's nothing here. So it's just these 2 impedances in series. How about for this? For here, you have 2 sources. Put the sources as short circuits. Find the, these impedances are in series parallel with this impedance, right? So that will be your X Thevenin, right, or Z Thevenin. How about your V Thevenin? You put a short circuit. Remember, you're finding Thevenin equivalent circuit, right? How do you find V7? Remember, V Thevenin is equal to Z Thevenin times I short circuit, right? So you can calculate I short circuit here. If you calculate I short circuit and you have your Z Thevenin, you can calculate your V Thevenin, right? Everybody remembers Thevenin, right? So the example is solved, so we can go through it, yeah. And then here, it's these impedances in series parallel with this impedance. There is no source in this case, right? Yeah. Just to make your life easy, actually, they made it easier for us here. What is, look at the numbers. If I put a short circuit here, what is V Thevenin for this circuit actually? Like if you look at the voltage between these 2 nodes, this voltage is opposing this voltage and equal exactly in magnitude and phase shift, right? So there will be no current flowing in this circuit. So since there's no current flowing in this circuit, what is the voltage between these 2 nodes? There's no current flowing. It's the voltage. If you have a voltage in series with many impedances, but there's no current flowing, what is the voltage at the terminals? It's the same. It's this voltage, right? Just because of the numbers here, it makes they made the 2 voltage sources exactly equal and opposite, yeah, right? But in the general case, you have to solve for I short circuit and solve for V Thevenin after that. So we will see that here in the Thevenin equivalent circuit. So again, they go through the positive sequence. The Thevenin voltage source is the pre-fault voltage 1.05 per unit from figured out with the sources shorted. The impedance at bus 2 is the sum and the parallel combination. So they go through and they describe where they came up with the numbers. But that's what we just did, right? It's just a Thevenin equivalent impedance and voltage source of the various circuits. Then what? That's all they asked for in this problem because we didn't take anything else actually. So reduce the circuit network to their Thevenin equivalent circuit as shown from bus 2. So first draw the circuit, draw the positive, negative, and 0, and then draw the Thevenin equivalent circuit. Now we have the Thevenin equivalent circuits representing the sequence networks for this system. Now what do? We have to figure out a way to connect them. Before we do that, the balanced fault case. If it's a balanced 3-phase fault, we said that we will, these are Thevenin equivalent circuits, right? If a fault is occurring on bus 2, and the system is balanced. The fault is occurring on bus 2 and the system is balanced. Remember we said that these sequence circuits are interconnected at the fault when the fault is unbalanced. If the system is balanced, or we have a balanced fault, then these sequence circuits represent the 3-phase system exactly as it is. right? And if I have a fault at a certain location, then I have a fault at the same location for the sequence circuit. So for a three-phase fault, three-phase balance fault, three-phase fault, or a three-phase fault to ground, it's a balanced fault. For a balanced fault, how do you calculate the fault current? We know that it's only the positive sequence circuit, right? So, but fine, you can put a short circuit on all of the sequence circuits. There will be no current flowing here, no current flowing here, since there's no voltage sources. We are left with only current flowing in this circuit, right? So it's this voltage source divided by this impedance. This will be the fault current at this location for a three-phase fault, right? It's, I mean, for me, it's basically the impedance diagram thing we did before, right? You have your impedance diagram and put a short circuit at a certain location. If you put a short circuit at a certain location, you want to see what's the voltage source, right? If you would like to see what the voltage source is, what the value of voltage. So we had, for your impedance diagram, we had what? We had the generator, impedance, 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 and then motor, impedance. If there's a fault here, how do you find the fault current? This is exactly the three-phase fault case, right? You can, you can do circuit analysis, you loop here and find the fault current, or you can do as we did. Okay, between these two nodes, find the Thevenin equivalent, and then after you have the Thevenin equivalent impedance and voltage source, put a short circuit here. I mean, it's the same. You found the Thevenin equivalent at these nodes, right? So put a short circuit at these nodes, and then you're done, right? So it's part of the process. So this is for the balance case. For the balance case, we ended up with 1.05. The current is 1.05 divided by this impedance, right? It's this impedance is J.13. So the per unit current is minus J7.558 per unit, right? I think this example was solved in the previous chapter, and the fault current was a lot less. It was the same example I think in chapter 7, I think, or in a different chapter. So basically we have it, or you can solve this circuit with, don't put a fault impedance. Don't make, if this is not a short circuit, if this is not a short circuit, then it's an impedance. Do you expect this current to be higher or lower? Much lower, right? If there's an impedance here, the current will be there's an impedance in the positive sequence circuit and there's no fault, then you expect the current to be much lower, right? So you can solve, for example, and put a load here, and then you can solve, for example, and put a short circuit. And of course, the current will be higher in the case of a short circuit here. So this is the fault current for a three-phase fault, and we know how to do that from our analysis. And fine. Now you have remember. Now you have the zero sequence current is zero. Negative sequence current is zero. I have my positive sequence current. It's whatever current that's flowing in this circuit. I have my positive sequence voltage. What is my positive zero and negative sequence voltages? They are zero as well. I have short circuits. I have my zero sequence voltage and I have my zero sequence current. They're both zero. My negative sequence voltage, my negative sequence current, they're both zero. I have my positive sequence voltage and my positive sequence currents. So you have your sequence quantities. You can use the matrix to construct your phase quantities, or you know that this is a balanced system, so you can just throw these away. And the solution is your phase A voltage is going to be phase A voltage would be this zero, because you have a short circuit on phase A, for example, but the fault current on phase A will be this current, in per unit, of course. This is stuff we did before, okay? Here. They just solved the circuit for you here, so they substituted. They wanted to calculate the phase quantities from the sequence quantities. They multiplied by the sequence matrix. And then here they wanted to calculate, because you will use this matrix, you will use this a lot. So if you are able to calculate your sequence currents, and you know your sequence impedances, you want to calculate the sequence voltages, right? If you are able to calculate the sequence currents, the currents in all these circuits, you calculated the current here, calculate the current here, calculate the current here. How do you find the various voltages? It's the current is flowing in this direction, right? The current is flowing, the zero sequence current is flowing in this direction, correct? This is the zero sequence current, yeah. So there's a voltage drop in the opposite direction across the Z0, right? So V0 is equal to, so V0 plus this voltage drop is equal to 0. So V0 is equal to negative of this, V across this Z0, right? Same thing in the negative sequence circuit. How about the positive sequence circuit? V positive is going to equal what? It's going to equal, this is V positive, is equal to this voltage source. This is current flowing where? In this direction, so the impedance in the opposite direction. So the positive sequence voltage is equal to what? It's equal to VF minus the voltage drop across the positive sequence impedance, right? Okay. So that's what we have. That's what this matrix is saying. It's saying that the zero sequence voltage is equal to negative of the Z0 multiplied by I0. It's minus the voltage drop across the zero sequence impedance. The positive sequence voltage is equal to the fault voltage, the voltage in the Thevenin equivalent voltage source in the positive sequence circuit, minus the voltage drop across the positive sequence impedance, and the negative sequence voltage is equal to negative of the voltage drop across the negative sequence impedance. Right? This is just representing these three circuits. Okay? And you will use it again because you will typically be able to calculate the currents, and then you will want to derive the sequence voltages from those. Okay, so you will a lot of times you will use this matrix. Yeah. Okay, so that's this one. Now we have to apply. Okay, we have a single line to ground fault. So what do we do? Before we were talking about the three-phase fault. If it's three-phase faults are balanced, the sequence networks are isolated. Fine, you calculated Thevenin equivalence because it makes your life easy, right? But now, single line to ground fault, anytime it's unbalanced, these sequence networks will be connected. How do you connect them is what we're going to learn now. Let's see. If I have a fault on, let's assume that the fault is on phase A. It does not really matter, fault on phase A or phase B or phase C. It's a single line to ground fault, right? If the fault is on phase A, then I have fault current on phase A. Do you agree? So there will be fault current on phase A, and here, so there will be. These are my three phases. So there will be fault current flowing from phase A through ground back to my source, for example, right? Remember that loop that we drew in the star? Okay, so current will flow from phase A. It fell to the ground, but there's an impedance. In the general case, there will be an impedance. I'll call this the fault impedance, ZF. Current will flow from my phase A through the fault impedance back to the ground network into my source and back. Phase B and C, we will assume that their currents are zero. Okay, so we will assume that the currents are zero in phases B and C, and we will figure out what this buys us. Okay, so what does this buy us? We will say that IB and IC are equal to 0. These will be certain conditions. These will be my input conditions. IB and IC equal to 0, and VAG, the phase voltage of phase A, is equal to the voltage drop across this impedance, right? This is phase A voltage between phase A and ground is equal to the current flowing multiplied by the impedance, right? So phase A, each of the fault cases will have some input conditions, and then we will do some manipulations and end up with output conditions that will dictate the connection between the circuits, okay? So these are the input conditions for the single phase to ground fault. Now I will substitute with what I know about sequence quantities and phase quantities, okay? So what do I know? I know that, okay, my sequence quantity is here, my phase quantity is here. I know that IB and IC are zeros. I will substitute with, remember, this is the sequence, inverse of the sequence matrix. I know I have phase A current. I know phase B and C currents are 0. So now I want to transfer from my phase quantities to my sequence quantities. I will multiply by A inverse. So this is my A inverse matrix. If I do this multiplication, I end up with what? And I0 is equal to 1/3 IA. I1 equal to 1/3 IA, I2 is equal to 1/3 IA. This is what, I mean, the condition of IB plus IB is equal to IC is equal to 0. Converting those from phase quantity to sequence quantity, this is what it gave us. That these are the sequence quantities, and they are all equal to 1/3 of IA. Right? So that's something we got. What else do we get? We have my second equation, phase voltage. Again, I will take my phase quantity, convert it to my sequence quantity. Right? What is phase voltage? How phase A voltage? I can represent it in sequence quantities as what? As zero sequence of phase A plus negative sequence of phase A plus zero sequence of phase A. Correct? So I can write this as V0, V1 plus V2. And then is equal to ZF, right? My fault impedance, multiplied by IA. IA is my phase quantity for phase A. How do I represent phase quantity in terms of sequence quantity? It's a sum of the sequence quantities. So IA is equal to I0 plus I1 plus I2. I just calculated I0 plus I1, I0 and I1 and I2 before, right? So I will now merge the two things together and see what it buys me. So we substituted with the sequence representation of phase A voltage. Substitute the sequence representation of phase A current. And then from what I know from before, I know that I0 equals I1 equals I2 equals 1/3 IA. So I can rewrite this second expression as what? V0 plus V1 plus V2 is equal to ZF, okay, multiplied by 3I1. Because I1 plus I2, I0 is equal to I1 is equal to I2. They're all equal. And they're all equal, and they're equal to 1/3 of IA. So take 3 here, multiply it by, so IA is equal to 3I0 or 3I1 or 3I2. So I substitute this IA that I had here with the sequence, one of the sequence currents, because they're all equal. And it's equal to 3 times I1. I bring 3 here because it's always convenient to see this 3ZF. We've seen it before many times. Right? So then I end up with what? V0 plus V1 plus V2 equals 3ZF times I1. Right? So what do these two conditions tell me? These are my input conditions, and these are my output conditions for the single phase to ground fault. I start from my Thevenin equivalent circuit. I will stop in a minute. Just give me 1 minute. I started with my Thevenin equivalent circuits. Remember, we calculated the Thevenin equivalent circuits for the system, correct? I didn't connect them yet, right? What do these two equations tell me? This equation tells me that all the sequence currents are equal. What does this equation tell me? It tells me that the sequence voltages, when you add them up, they will equal the 3 times the fault impedance multiplied by the sequence current. So one way to represent that is this. I put the 3ZF here, and if I have the sequence current I1 flowing through it, I know that the voltage drop generated by I1 or I2 or I3, because they're all equal, flowing I0 or I1 or I2 flowing in this 3ZF will equal the 3 voltages added together, the 3 sequence voltages added together. So this is what these two equations give us. So they allowed us to connect the sequence circuit, the Thevenin representation of the sequence circuit, in a certain way. Now you can solve. What is the what's the current in this circuit? It's this voltage source divided by this impedance in series with this impedance in series with this impedance in series with this impedance. You've calculated I0, you calculated I1, you calculated I1 and I2. What are the sequence? What we need to come out of this is the sequence current and sequence voltages, because then you take them, convert them back to phase quantities. So you've calculated the sequence currents. How do you calculate the sequence voltages? It's the zero sequence voltage is equal to negative of the voltage across this impedance, negative of the voltage across this impedance, VF minus the voltage across this impedance. Or basically you apply the matrix that I showed you before, this matrix here, after you calculate the sequence currents, right? And so is it okay? Everybody okay with this? So we'll stop here. So it's the same. I mean, it's a very similar process for the double line to ground and double line faults. We will just have some inputs, conditions based on our assumptions. You know, other phases with no fault current will have zero current. Will have zero current flowing through them. And then we will look at calculating the fault voltage. What is this fault voltage equal to? It will equal to the current coming from, if it's a double line to ground fault, it will be the current coming from the two phases flowing into the fault. And we will use that to come up with my output conditions. And these output conditions, we will formulate them into a circuit connection between the sequence networks. So really, it's if you have the sequence networks from the Thevenin equivalence, then it's something, okay, you just apply. This is what you apply when you have a single line to ground fault. This is what you apply when you have a double line to ground. And this is also in your equation sheet, which is in front of Sarah, so she can tell us everything about it next time. So we'll stop here, yeah. And we will wrap up this